Hello, welcome back. I picked this number 26 out of chapter 5, 5.1. It's worded a little funny. It says a mass weighing 4 pounds is attached. I'm sorry, that's not what it says. A 4-foot spring measures 8 feet long after a mass weighing 8 pounds is attached to it. What I got out of that is that an 8-pound mass stretches the spring 4 feet. And of course, if it's an 8-pound mass, the mass is actually a fourth, 1/4. If it stretches at 4 feet, K is 2. The 8-pound force stretched at 4 feet, K is 2. And then there's this sentence. The medium through which the mass moves offers a damping force numerically equal to the square root of 2 times the instantaneous velocity. Wow. So the damping force is this number, and it says it's numerically equal to the square root of 2 times the instantaneous velocity. So that's a long sentence that tells us beta is the square root of 2. That's the way they're worded. You'll have to get used to that, but it's easy. All right, so we have our mass, our K, our beta, and our differential equation. I write the auxiliary equation. You should do the quadratic formula. And get the roots here. I'm going to skip that part. The roots were, the roots was -2 times the square root of 2, and it's repeated. So this is one root, repeated root. So, and by the way, when you also read the problem, I think it said, let's read this. It said, the mass is initially released from equilibrium position with a downward velocity of 5 feet per second. The mass was initially released from equilibrium position with a downward, remember down is positive, a downward initial velocity of 5 feet per second. So those are the initial conditions. We found M, beta, and K. We wrote the D. We wrote the auxiliary equation. I found the root. It was this repeated root. So the answer is x equals c1 e to the -2 square root of 2t. Because it's a repeated root, you have to write c2t e to the -2 square root of 2t. And that's the position equation. With these initial conditions, we can try to find c1 and c2. Let's go ahead. I am going to need x prime, but let's go ahead. Plug in 0 and we get 0. Let's see what happens. If you plug in 0, e to the 0 is 1, so there's c1. E to the 0 is 1, but that t is a 0, so that zeroes out that term. So very quickly, c1 is a 0. We are going to need x prime to use the other initial condition, so here we go. X prime is the derivative. The derivative is an e function. That's pretty easy. The chain rule does spit out -2 square root of 2 times c1 e to the -2 square root of 2t. There's a little product rule here. The derivative of the first is a c2 times that e function, and then a c2t times the derivative of the e function, which spits out the c2t e to the -2 square roots of 2t. Little product rule there. When you plug in a 0, the derivative is 5. That was from the initial condition. When I do plug in a 0, I get e to the, I get this term. Now it turns out, remember c1 was 0, so that term's 0 actually, sorry. I get e to the 0 times c2, and that t is 0, so that term zeroes out. This c1 was a 0, so I just discovered c2 is 5. I found c1 and c2. The answer is, c1 is 0, c2 is 5, 5t e to the -2 square root of 2t. By the way, we had this one repeated root. This is a critically damped situation, which, if you remember, quite resembles the overdamped situation. In fact, the graph of this looks like this. I used my graphing calculator, and I discovered, remember, it was released from 0 with a downward push of 5 feet per second. Listen, this is down. I'm sorry. Down is positive. So it had this downward push, and guess what? It never makes it back to equilibrium. The damping it doesn't oscillate. It had this downward push, the spring pulled it back, and it's damped so much that it doesn't pass through equilibrium. It just dies out here and approaches zero. The question in the book did want to know when did it reach its maximum displacement from equilibrium, which we no longer really call an amplitude here. We don't have a wave, we don't call that an amplitude, but when did it reach this maximum? So I used my calculator, and I'd found out the answer to be t equals 0.35 seconds here, and this maximum x distance here was 0.65 feet. So, that was fun. That was a nice example of a critically damped situation. I helped you find C1 and C2 with the initial conditions. What I didn't help you with was the quadratic formula which led to this root, but you can verify that, this repeated root. All right, we should do another one.